For horizontal flow, it doesn't take much time, but if it's like 0.1 degree up, yeah, it takes some time. So this case is horizontal flow. I think even if you get stuck whatsoever, it may take the first one double about like 5 hours, but just 1 hour for this one everybody. Together is 6 hours, so it's fair because this 3 credit hour class should have double time for the homework and the material study. All right, all these things they are the same as double half-pi. Review this if you cannot do it. The boundary condition, how to solve it, the way to do critical height, equilibrium height, they're the same, just different equation. Got it? Okay, let's move on. So after we have the film, the objective is to get pressure drop. Okay? To get pressure drop, double Hubbard 1975 and Nicholson suggest pressure drop along the slab unit length like that. So when I look at this equation, that term is delta P sub A, right? That is hydrostatic head just in the slug body, right? LS, slug body. That is frictional pressure loss just in the slug body. Okay. By the way, as a rule of thumb, without doing any calculation, okay, if you have up, down geometry, when you go up, we have slug flow, down we have stratified flow. You already know that, right? So what you can assume is, without any calculation, when it go up, have pressure drop. When it go down, no pressure gain. Okay? When it go up, we have pressure drop. But when we go down, we don't have pressure gain. Okay? That's the rule of thumb. And you can actually prove it. But if I give you that homework too, maybe it's like a combination of stratify and slug together, maybe it's too much. But I think you can do it pretty fast. If you program everything in the calculator and do it in the exam, how about that? Is it better? How do we do these things in the exam quick? LS or rho S, is that a way to calculate it quick? Yeah. Okay, you can pre-program your calculator. Tau, X, everything can be get pretty quick, right? This equation, do we need to know anything about film profile? That one, VRTBE, right? That comes from film profile. The rest, nothing to do with the film profile. Okay. This is double Hubbard version. What about Taitel-Barnea version? Let's give something. And actually it's just next page, so we don't really skip anything. So substitute everything. We have that, right? Substitute x value divided by a. Rho g sin theta is a pressure drop due to the change in elevation, pressure drop due to friction, pressure drop due to picking up or acceleration. Taitel-Barnea didn't use the same thing. No acceleration term, because to add acceleration term over that is not correct. Okay. So Taitel-Barnea use this global force balance, rho u, sin theta Lu. Okay. Instead of rho s, g sin theta Ls. So they consider everything that have mass if you have gravitational pressure loss. Friction in the film zone, friction in the slab body zone, Ls, multiplied by that. And this is a friction in the film zone. Film has top part and bottom part. Top part is gas, Sg, La, tau g. Bottom part is F. So that is like stratified flow. If I assume that film height is constant, I can do it, right? Okay. So let's say I don't want to do film profile calculation. I want to get it quick. So step 1, I may do okay. Let's get slug frequency. From slug frequency, let's use another cross relationship to get slug body length, 30 diameter. Based on those two, I have too much information already. Then I have to select the height that make the mass balance, right? But if I assume that the height is uniform, I can just go back to my mass balance equation. Okay, mass balance equation, and I don't do integration. I remove that and I say multiply by LF. HLTV is constant. Okay, and use relationship with X or something. So this term is known. This term is known. This is known. This is known. Known. Cross relationship, 30 diameter, cross relationship, okay. AP is known, that is known, that is known. HLTB and VLTB is kind of unknown, but okay. L sub F, we can use another cross relationship to get frequency, and from frequency we get this. So it will be those two terms that is not known. What's your question?
Yeah, so you are talking about the assumption that we assume HLTB to be constant. What part of the profile do you look at?
Instead of the bullet shape, instead of that, we say is this.
Okay.
Oh, no, we didn't actually say that. We said is that. Okay. Average, kind of average, so that it has mass balance. So typically we use either frequency, cross relationship, or slug length cross relationship. We don't use both at the same time because it will be too much. Okay. But if we use both at the same time, then we don't need to solve height. If we use just one of them, then we have to solve for height, right? But if you use both at the same time, okay, I get the solution that I get VLTB multiplied by HLTB, not individual term, just from that equation. Because the rest, I assume that is known, come from cross relationship. Is there a way to solve it? Okay, let me go back to this one. Is that going to help? Or is the same equation? Maybe it's the same equation. It doesn't. Maybe it doesn't help. I don't know. Okay. Is there a way to assume that the height is constant, and we can solve for it? Skip the RKF profile.
Only if we use the numerator.
What?
Only if we use the numerator of the equation to calculate the
Okay. Equilibrium liquid height. That would be minimum possible height. Right? Okay, that's one way to estimate it. Okay, maybe we have to use that because we don't know the velocity in the film. Okay, let's take a look at the pressure drop thing. How did they do it? And why have the acceleration pressure loss over there is not good idea. Okay, let's take a look. When you look at this, Taitel-Barnea doesn't have acceleration pressure loss. Okay, and that maybe compensate for the increment in the height when we pick it up, pick liquid up. Let's take a look. on their reason, okay? Rho U is a weighted average based on holdup of total slag unit liquid holdup, okay? If we neglect the pressure drop along the bubble, okay, double Hubbard neglect that, right? So we don't have that. I mean, LU doesn't have the part that is a film. So we have this equation. This equation has frictional pressure loss due to slug body, gravity due to the slug body, and rho g sine theta multiplied by that is gravity due to the film, right? Okay. But doesn't have gas. Doesn't have anything about gas. And we have friction due to liquid phase. And in the slug body, and friction due to the film. Not tau G. Tau G is gone. Okay. HLSU most of the time has something to do with rho G, right? You see that rho G? But this time, rho G doesn't appear for the film part. It has just rho L. So we don't consider the density of gas because it's so small. The friction due to gas is so small. So full form is correct. Approximation is also okay. Okay. This thing is the same that double Hubbard used. It should be the same, okay, because they calculate the same thing. Okay, but it's not quite. Let's take a look in detail. For the film full momentum equation, we have this. Okay. Assume tau I equal to 0. That term is gone. Pressure drop in the film is negligible. That term is gone. Okay. Then we have just this. Okay, by the way, you already know how to calculate the film profile. You already know how to calculate the slug, the pressure drop. This part that I'm talking about is about like what is the difference between double Hubbard pressure drop and Taitel-Barnea pressure drop. They're not the same. There has to be something, right? This is the explanation. Okay. All right. By neglect tau I and say pressure drop in the film zone equal to 0, we get simplified form that equation. So this equation have what? MA term. The rest is the same, right? Except those things. Okay. Integrated with respect to film length. Okay, put integration with respect to L over there. Like cover everything. Cover everything on the left side and the right side we have that. Okay. Next step, this part I just copied from the previous page. Okay, this part just copied from the previous page. So we try to integrate it. Now I take a look at this term. LF, SF over AF, okay, integrated with respect to Z. That is here. So this term becomes that one. Alright? Rho LG sine theta, that term becomes that term. Good? Okay. What about the rest? Why do we have different limit? So it's kind of that, kind of cancel with that. It's not cancel, but okay, mathematically we change the integration limit. Instead of integrate with respect to Z, we integrate it with respect to VF. So the top value instead of LF has to be VF at LF. at the end of the film. At the end of the film, relative velocity is VTB minus VRTB. At the beginning, VF or relative velocity is VTB minus VLLS. Okay, and integration limit change to dBF. The last term, same thing, that kind of cancel with that, so we change the integration limit. Instead of dz, now it's DHF, or film height. The top limit will be film height, where z equal to LF, and the bottom limit stay the same, like height at z equal to 0. No question? Or you have question? Not yet? Alright. Multiply HLTB on both sides. On the left hand side and the right hand side. Okay, on the left hand side, we have just that term, right? That term multiplied by HLTB. Okay, HLTB, it becomes this term. Okay, instead of HLTB multiplied by VF, it will be VTB minus HLS, or VLLS, HLS. How can I do that? Relationship from X, right? You still remember relationship from X? I mean, we use very frequent, like that one, that equation. Okay, because of that, I can make a change to this. Left hand side. Now, let's do some integration. I put that term outside. Okay, that term outside, because none of this is a function of z, right? Rho is not a function of z. VTB minus VLS is not a function of z. HLS is not a function of z. So I can move the whole thing out. And inside will be, the integration result will be just that. Do the math. VTB cancel with VTB. I get that. Okay? Good? That is the integration result of the left hand side. What about the right hand side? Right hand side, I copy everything here. Okay? Of course, I can change the integration limit, right? Because I have partial derivative of h with respect to z and integrate with respect to dz. So I can change to that. No problem on this equation yet. Do you? Not yet. Left hand side equal to right hand side. Okay, left hand side equal to right hand side. Left hand side is rho delta v, h delta v. Rho delta v, h delta v. So that is the green one. Rho delta v, h delta v. Left hand side equal to whatever on right hand side. Okay. That term continue, that term continue, that term continue as usual. Substitute this into global force balance. That is already neglect the pressure drop in the bubble. Okay. Global force balance that we neglect the pressure drop in the bubble. Substitute where? Where do we do substitution? So I'll go back. You see this equation? Okay. So which term is the new term that we have? Oh. So if I just copy it, that, is that the same as this? H dz, okay. So it's the same thing. I substitute it in. Okay, so basically I change from the brown one or the orange one to the green one, right? And they are consistent because the way that I derive this, I derive it based on neglect the pressure drop in the gas zone, and this equation is also for the no pressure drop in the gas zone too. So it's the same thing. So I can substitute, change the orange one to the green one. Or do you think it's brown? It doesn't matter, right? Okay, we have this one, this equation. Copy this equation to the next page. Okay, this is equivalent to equation in your book. Check it. 3.147, right? What's 3.147? 3.147 is with delta mix. That one, right? That is Douglas-Hubbard suggestion. Douglas-Hubbard suggestion is like, okay, hey, pressure drop in the film, we neglect it. Okay. Why? When I do that, this thing, I put over here that the equation should be the same from Douglas-Hubbard, but it's not. The last term containing cosine theta is missing in the Douglas-Hubbard term. Douglas-Hubbard has that, but not that. Okay. For vertical flow, cosine theta term becomes 0 and global force balance method will be the same as Douglas-Hubbard. Okay. Where tau I, tau G, and dP/dz in the film region are neglected. So Douglas-Hubbard momentum balance is that. See, it has every term. That one, oh, let me erase this. So this term, same. That term, same. That, same. Extra term. What is that extra term? It has something to do with cosine theta on the height, right? The change of the film height. If the film height is same everywhere, we don't have that term. Is it cosine theta? No, I'm sorry. So it has something to do with the film height, even if it doesn't change or anything. DHF. Okay. So if there is no change in the film height, then this equation becomes 0, like if it's straight. But there's a change, so we have this term. Okay? Question? Not yet. Which one do we use? Taitel-Barnea. Okay. I copy this equation again and compare against 3.147. Okay. Show that it's not the same. To make it the same, delta P mix over there should have two terms, not just one term. Right? The first one is the pressure drop due to elevation. The second one, which has something to do with those cosine theta, is negative. Is it?
So, excuse me, you said pressure drop due to the acceleration or?
The first term is picking up.
Okay.
Acceleration or pressure loss. Right? The second term is what? Let's take a look at the sign. Rho G cosine can be taken out. Right? I'm put it back to dz coordinate so that we have dHF by dz term pop up. dHF by dz term is negative. Okay? When we integrate from 0 to LF, we integrate backward. Okay? dHF by dz is negative. So this whole term is negative. Negative of pressure drop is a pressure gain due to the increase in the hydrostatic head. As we move to the right hand side, there's a gain of the hydrostatic head. It's not in Douglas-Hubbard equation. Okay? But don't think that Douglas-Hubbard model is bad or anything. I don't think if we don't have Dr. Hubbard, I don't think we have Taitel-Barnea model. That's the first step, and this is kind of second step. Okay. Yes.
Excuse me. Please, if just I'm confused a little bit. If we move in the direction of Z, given the film profile goes like this, are we gaining in the hydrostadia or are we decreasing the hydrostadia?
Okay, good question, but it's not quite what we are looking at. What we are looking at is actual pressure drop over a length in flow direction. Within the flow direction, we should have pressure drop from one point to another point, right? You agree with that? From that equation, with all these derivations, it shows that, hey, there's a term that has something to do with this part. Okay. Sometimes that pressure drop term has to be calculated from the moving coordinate system, and moving coordinate system is kind of opposite. Even though it is from that, but it doesn't change the fact that we are calculating the actual pressure loss. And it doesn't change the fact that that term is negative by itself. So this means when we move to the right hand side, we gain the height on the film that causes the gain in the pressure or negative pressure loss. Okay? What you try to do is pressure drop along the Z direction, right? We don't do that because that's opposite to the flow direction. This the other piece of U is a pressure drop in minus Z direction or in the flow direction. Okay. This delta P max and delta P sub A. In the book, I just copied from the book, okay? Delta P max is always less than minus delta P sub A. Okay? Delta P max is what? Combined between acceleration or pressure loss and the gain part. Delta P sub A is just the loss, but not the gain. So this means actually we lost pressure a little bit less than what we think we should lose. See what I'm saying? So if we use pure Doppler-Hubbard model, we use this equation, we have too much pressure drop. You get too much pressure drop because you didn't consider the pressure gain due to the change in the film height, and that is the change in the film height. Okay. All right. Let's take a look at a little bit more detail. So this comes from Taitel-Barnea paper. The actual paper we have location A, location B, location C. Okay. The nomenclature is about the same as what we use in the lecture and in the book. Not quite exact, but okay. From here, the pressure drop equation, they use this one for their force balance. Okay. So this is a little bit different subject. But when I actually go into the paper, they show this equation. Okay. This equation, when I look at it, okay, this is Taitel-Barnea momentum balance without considering dPdZ in the film zone and tau G in the film zone and tau I in the film zone. So it's exactly the same thing that we are looking at. Okay, same thing. Okay. And another form of the detailed momentum balance equation is this one. So what is this one? So the top one is pressure multiplied by area at point A. That's pressure multiplied by area at point A, right? Flow direction is this one. Plus kind of hydrostatic head, Fi. What is Fi? Let's erase this. You see this Fi? Fi is that point at point A. Fe is at point B. So this is the height at point A. Pressure plus hydrostatic head at point A, like total pressure, minus pressure at point B plus hydrostatic head at point B, okay, equal to the difference in force, rho g sin theta, okay, so PA, PB sin theta, z is in this direction, okay, so actually if you move everything to the right hand side and make it 0, the sign is the same as what we have earlier, okay. So on the left hand side, when it moves to negative z, it's actually positive, but if you move to the same side, it will be negative and that will be positive, so the sign is the same. So this term, the gravitational force is in the plus z, so it's positive. Tau s plus z, and that term, accelerational thing, is, we have it here as plus z. Okay, this is the way that Taitel-Barnea do the momentum balance. Okay, the change in the pressure and hydrostatic head is due to the gravitational term in slab body. Friction from the slab body and accelerational from the frame, from that velocity to that velocity, okay, add them together is delta p sub u. Then this equation is, we have the first term, second term, that term, and that term. So this is 3.149, right? Is it? This is that equation. Maybe too much. So from this equation, let's compare against the original force balance. Okay, this is original force balance and this is that equation. Compare them. We keep in mind that that equation is from the original form is that one. Okay, so this equation is the same as that. All right, we consider all the film, everything except the gas part and tau I. Okay, now let's do some mathematic trick to rearrange it and show you something that what's really happened here. You see that term? Cosine theta term from z equal to 0 to LF of rho g h LTB cosine theta. Okay. This term is that minus that. Okay. What am I doing here? I just split the term. Okay. This is from HF as z equal to 0 to HF as z equal to LF. Okay. I can split it into HF 0 to LF and 0 to kind of z equal to 0. So I integrate from 0 to HF minus from 0 to HF and z equal to 0. Let's just split it. Okay. And previously you already know when we discussed about the hydrostatic head. This hydrostatic head thing comes from this kind of equation that have delta H and B. You remember that? Okay. Come from delta H and B. So when I look at this equation, you see this term, 0 to H FE of H LTB dF. Okay. This term or this one. So this term by itself, I can integrate it. Okay. But this has to be change HLTB to AF over AP. I take AP out. AF, I have to integrate it twice. or double integration from 0 to HF dy and 0 to FE DHF. Okay, that is kind of double integration. That B change with height. Okay, y is a height coordinate. So this whole expression is just the expression for HLTB DHF. Okay, at z equal to LF. Okay, we have HFE. At z equal to 0, we have HS. Okay, so that's allow HLTB equal to HLS and z equal to 0. Now let's do some trick on the integration. For that integration, HLTB DHF, I have integration with dy dx. Now I can swap it and make it to be dh dy. But the integration limit has to change. Become that. Okay. With this, substitute it back, it explains the difference in the equation. Okay. But we will continue this next time. This time's up. Alright. It's 12:19, so is it okay that you go like 30 seconds earlier? Maybe not even 30 seconds, maybe 10 seconds. Okay, see you next time. Thank you for coming.